Hey everybody, welcome back to another round of physics, and yeah, let's get going. We're going to continue our discussion about capacitors, and in particular, I would like to discuss three different topics. Number one, how to calculate the energy stored on a capacitor or within a capacitor. Number two, using that result to get an idea about what happens when we have multiple capacitors in a circuit. And finally, we'll have a brief discussion about how the insertion of extra material within the volume of capacitor changes the ability of the object to hold charge. Okay? So yeah, let's get going. Just as a reminder, we are thinking about capacitors as conceptually being two conducting plates, and then we have to connect it to a circuit in order to force charges onto a top plate, thereby expelling the same charges from the bottom plate so that an electric field is generated between the two plates. Now, normally we do this by hooking it up to, say, for example, some battery. A battery is an object, a chemical object, designed to maintain a difference in potential between the high terminal side, so we'll call this V high, and a low terminal side, V low. Okay. And in particular, it's built to prevent the charges from moving within the battery. Okay, we'll consider it like a black box. So it's not like the positive charges can go downhill within the battery. Rather, you have to give it some path for those positive charges to continually roll downhill. Now, in this circuit, those positive charges deposit themselves on the high plate. And because of the presence of those positive charges are excluded or rejected from the bottom plate, so these charges, and thereby completing the circuit. Now, these bottom plate ends up becoming negative. Now, I'll have this at the end, a full table, but you can imagine drawing a battery every time you want a circuit is not necessarily time efficient. And also, I appreciate the compliments to my artistic abilities. However, I think we would argue that that looks like a junky battery. Usually, how we indicate batteries is a series of parallel lines, one being long and the other one being short. Okay. Now, I tend to draw just two, but some places will end up drawing a set. They'll draw a couple of sets of these. Okay. And how we interpret that is that the long bar is the high potential side. The short bar is the low potential side. Okay. So if that helps, you can always label and say, okay, high and low. Incidentally, also, in just regular batteries as well, when they put a positive and a negative, they are not referring to the charge, but they're referring to a high and a low potential side, just like I did 10 seconds ago. Okay, so just be careful about that. Well, the question is, that happens. Let's say now I disconnect the battery. I remove the battery from the circuit, so there is no way for these positive charges to actually, get back to combine with the negative charges, for lack of a better word. You know that if you took the battery out and then you end up, actually this is a good point, if you take the battery out and you string a wire across the gap, then these positive charges, which are not physically able to jump the gap, you give them an alternative path for them to flow back to the negative charges. And of course, as each positive charge flows around to combine with the negative charge, the electric field, which starts out strong, slowly decreases in its value until it disappears, as more and more of those charges move around the circuit and recombine with the bottom plate. Okay? Now here's the first question. Imagine, let's say, for a brief instant, we'll put the battery in. Okay? And usually instead of calling it V high and V low, you'll see me write it as something like V battery. What I mean is that the change in potential from the low side to the high side is, I call that V battery. Okay. Now, if you prefer, if you like to think of it starting at 0, that's perfectly fine. We will go ahead, and this is another symbol that we'll see as we go forward. We'll go ahead, and this symbol simply means grounded. And how that helps us is that you can think of that as being the reference point from which we will measure the other potentials within the circuit. So if I ground the red wire on the bottom part of this circuit, then you know that the potential on the blue wire at the top must be the same as the potential of the battery. We go from the low side of the battery. You can imagine this almost being like an escalator. Excuse me. This is at sea level, this bottom piece, and then you ride an escalator to get to a higher elevation, a higher potential. And then now that you're at a high potential, you can imagine yourself rolling back downhill. Now, the first question I should ask you, okay, let's say I have a fully charged capacitor. What is the potential drop if I moved from one capacitor plate back down to the other? Yeah, good. Also, it equals the potential of the battery. You can imagine if the battery represents some sort of escalator taking you from sea level up to some higher potential, and you can imagine, let's say the capacitor, I don't know, I'll use this later, but I like to think about waterfalls as well. Not the TLC kind, but like physical waterfalls. But you can imagine that if I start at, say, a high elevation and then I somehow manage to get across to this lower elevation, I'm back at sea level. And so at this point, the potential across the capacitor is equal to the potential across the battery. And in fact, that should make some sense, is that when the capacitor is fully charged, no more charge wants to leave the battery and deposit itself on the capacitor plate, which means nothing is moving. There's no current moving anymore. And this top wire becomes an equipotential. It is the same potential at any point along the wire. Well, similarly, on the bottom part of the circuit, because of how the capacitor works, if no additional charge is being deposited on the top plate, then no additional charge is being expelled from the bottom plate. So if nothing's going on in the top part of this circuit, nothing's going on in the bottom part of this circuit, and so again, the bottom part of the circuit becomes an equipotential. Well, then, if it's grounded, the bottom part of the circuit is grounded, that means every location on the bottom part of the circuit is 0. On the top, every location is at a potential of V battery. And so the jump across the battery must be equal to the drop across the capacitor. Pretty cool, huh? Okay, so that's the first of it. So we wanted to argue, and incidentally, this is what I mean when a capacitor is charged. You'll see this phrase a lot in the sense, what we'll say is a capacitor is charged using a battery, a 9-volt battery. And what we mean by that is that you can then say immediately what the potential drop across the plates has to be. Of course, if you're given a value of the capacitor, then knowing the potential drop and the value of the capacitance immediately will tell you how much charge is stored in the capacitor itself. Just as a refresher, what's the relationship between the change in potential across the capacitor and the amount of charge that the capacitor holds? Good. Hopefully you remember that is the definition of capacitance. It is the amount of charge divided by the potential drop across it. Okay? If you don't have this memorized, get it memorized. Okay? If you don't plan on taking any other physics course or engineering course ever, sorry I scared you off, but if you do, you need to have this memorized because you will use it repeatedly in any circuit course you see. So let's go ahead and get an idea now. Okay. First of all, let us pretend for a moment that we are going to remove the battery from the circuit. We have fully charged up our capacitor, and from a very conceptual standpoint, we'll pretend that we removed the battery. Okay. That's the first part. Now, the second part, let's pretend that I run a wire from the high capacitor side, the high potential side, back down to the low potential side. So I'll do that in green here. And you can imagine what's going to happen. We know the potential going from one side of the capacitor through the other side. So imagine that this charge now has a path to flow back to the low potential side. So it goes wee, 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 all the way home. Now you can imagine when this charge moves all the way through that potential and releases a small amount of potential energy, it's equal to the small charge that moved times the potential difference of the capacitor. Okay, good. But now, because that charge has moved from one point to the other, now the charge on the capacitor plates is slightly decreased, right? Those two charges have, for lack of a better term, recombined. And so the surface charge density has slightly decreased. But if the surface charge density has slightly decreased, so has the magnitude of the electric field. And because of the magnitude of the electric field changing, the potential difference between the capacitors changes. And there is a slight less energy stored on the capacitor plates. Well, I shouldn't say on the capacitor plates. I should say in the electric field. Well, let's go ahead. Now we have our specific setup. We know that a small change in potential energy is caused by moving a small charge across the potential difference of the capacitor. But we will go ahead and use our expression for capacitance and substitute in that expression for the potential difference between the capacitor plates. Namely, the potential difference is given by the charge on the capacitor divided by the capacitance. Okay, so we're taking that C equals QV and we're rearranging it to say the difference, the potential difference across the capacitor is Q divided by C. So we're going to go ahead and substitute that in. Now, you can imagine for that first charge that I move, we have that the capacitor charge is the total. And so you can think of that first little charge that I move across the capacitor total. And so I think about the energy as simply being the area of that rectangle divided by C, and that will tell us how much energy is released. But because now I have moved a small infinitesimal charge, the charge on the capacitor has decreased by an infinitesimal charge as well. And so then we rinse, wash, and repeat. We move the second infinitesimal charge, and we find that the second infinitesimal charge releases a certain amount of energy. And when that energy is released, there is a new charge on the capacitor, et cetera, et cetera. And so you can see where we're going to go with this. Okay? We are going to go ahead and sum up all of those infinitesimal contributions. Now, how we sum that up, because we are moving tiny charges, okay, we can do an integration. So evaluating, okay, we get something that says Q squared over 2C. Now, I apologize. I've dropped my limits of integration here. Okay? And what we have to remember is that we started off with a total charge of Q, and we ended with a total charge of 0. And so we could evaluate at the upper limit, we could evaluate at the lower limit, and we get that the change in potential energy is equal to negative Q squared over 2C. But we're going to use that idea now. Okay? So that's it for the energy stored in a capacitor. And incidentally, that is the same regardless of the geometric shapes, regardless of what kind of capacitor we're dealing with. The expression for C might change depending on, what capacitor, but the equation for the potential energy does not. And incidentally, you say, wait a minute, Greg, we had Q squared over 2C. Please bear in mind that's the max. That's the starting charge, or maybe it's the maximum charge if the capacitor is fully charged. Okay. But we could also use this idea that C is Q over V. Okay. So we could substitute in something like that's not right. C times V is equal to Q, and we could substitute that into this expression. So we could end up with something that says, for example, 1/2 CV squared. So this upper expression, if I know how much charge is on the plates and I know the capacitance, this top expression might be better suited for my needs. But let's say, for example, I don't know how much charge is on the capacitor, but I do know the potential difference of the battery used to charge the capacitor. Then maybe the second expression would be more appropriate. And of course, yes, if you get really jazzed, you could see, well, wait a minute, if I don't know those, okay, you could say, well, 1/2 QV, say I don't know the capacitance, I could use this to substitute in for C and get rid of, C altogether, and you end up with something like QV. I have to admit that QV is probably the least useful of these three expressions, just because in general you tend to know what the capacitor is, particularly in practical problems. You are manufacturing something, you get to choose what the capacitor value is. So this third one tends not to be as helpful. Okay. We will go ahead and move on to the second piece of this lecture, and that is combining capacitors. Now, this is not always useful, okay? It depends on the situation, but sometimes this will be helpful to simplify circuit arrangements. And I will give this proof thinking about energy. So let's first of all introduce two terms. The first term I'm going to introduce is what's called series. Okay? We talk about circuit elements as being in series or in parallel. And first of all, I'll visually give you an idea. Incidentally, I am using the electrical symbol for a capacitor, which differs from that of a battery. These are two parallel lines, but notice that they are roughly the same length. Okay? So parallel lines of the same length represent a capacitor. Parallel lines of different lengths represent a battery. Yes, sometimes you have to be careful if you're drawing fast. I have seen textbooks use a straight line and a curved line also to represent a capacitor. And I suspect that that is to make sure it's not confused with the battery. I don't care which one you use. I tend to use the parallel lines of equal length only because that's what I, for lack of a better word, grew up learning. So here I've got two different arrangement of capacitors. Okay. Now, for a series arrangement, how we will define it in this class is that in order for charge to go through one capacitor, say this one, it must go through another capacitor. Now, again, I'm using this in through because we know as good physicists that what happens is positive charge gets dumped onto the capacitor of the first one. Let's say we hook this up to a battery for illustrative purposes. Okay. And so positive charges get dumped on the first one, which means positive charges get expelled from the bottom plate, which ends up becoming negative. But those positive charges that are being expelled end up congregating on the top plate of the second capacitor, which, of course, causes positive charges to be expelled from the bottom plate and eventually returning to the low potential side of the battery. Okay. Now, here's the question I have for you very quickly. Okay. Thinking about this arrangement of capacitors, again, what we call it in series, how does the charge on the top capacitor compare to the charge on the bottom? And by this, usually when we talk about the charge of a capacitor, what we're talking about is the net charge on one of the plates. Yeah, good. By nature of how capacitors work, the charge, when capacitors are in series, the charge on the first capacitor ends up being the same as the charge on the second. And again, you can see that just by virtue of how the capacitors work. If charges are expelled from the first capacitor, the only place for them to go is the second one. Good. Okay. So let's think about how we can use that to simplify this expression. And we will return to the parallel one in a moment. Let's pretend for a moment that we are interested in finding the total potential energy stored in this arrangement of capacitors. Well, you know that the potential energy, the total, should be the energy stored in the top capacitor plus the energy stored in the bottom one. Well, now we will go ahead and use our handy-dandy expressions for capacitors, namely, and please bear in mind, right now we have a relationship between the charges on the top and bottom capacitors. And so I will go ahead and choose the potential energy expression that has the charges and the capacitances. If I substitute that in, we have something that says that the charge on the top capacitor squared, and I'll call this C top, plus, now here we recognize we'll take advantage of the fact that because they're in series, they have the same charges. So I'll rewrite this as, instead of using the bottom, I'll again write it as Q top, and this is the capacitor, bottom capacitor. Now, we can't go any further here. But here's the next thing. Let's say, well, we have to take a byline. Let's say instead of using two capacitors, I would like to model this circuit as being a single capacitor, what I will refer to as CEQ, the equivalent capacitance. And the question is, what must the value of my equivalent capacitor be so that this circuit on the right-hand side stores the exact same amount of energy as the circuit on the left-hand side? That's the question that we want to answer. And so we see that, hey, this equivalent capacitor, same battery, I want to store the same amount of potential energy. So I'm storing the exact same amount of charge. And so what ends up happening is I will again use my expression for potential energy. I would like this to be equal to 2CEQ. And now we can simply say, goody goody, I have these two expressions equal to each other. Excuse me, maybe I should have written it up here. We have a goody goody moment. And we see that in order for these two circuits to store the same amount of energy, and I should say the same amount of separated charge, the value of the equivalent capacitor must satisfy this relationship. In other words, the inverse of the equivalent capacitance is equal to the sum of the inverse of the capacitor values. Now we rewrite this. We can write this more succinctly. We say the equivalent capacitor is equal to the sum 1 over where these are the individual capacitances. And that's perfectly expandable. We can expand that not only to one capacitor, it could be 10, it could be 15. So long as they're in series, we can replace multiple capacitors in series with a single capacitor. The circuit will operate exactly the same. We will not change the behavior of the circuit at all, as long as the equivalent capacitance obeys this relationship. Pretty cool, huh? Well, you say, Greg, you had another example. You said, hey, what about if we have capacitors in parallel? So I'll call this, I don't know, C right, and we'll call this one C left. Okay. And here, let's again imagine that I charge these by connecting them to a battery. And now here, we do not want to assume that these two capacitors are of equal value. Okay. That's putting in an extra assumption that we do not need. Okay. Rather, let's ask a different question. Because these two capacitors have different values, or at least we assume they're different, we cannot assume that they store the same amount of charge. But there is something that's the same between these two capacitors. Yeah, look. Both capacitors have a connection to the high potential side. Both capacitors have a connection to the low potential side. And so the change in potential across the change in electric potential across the left capacitor must be the same as the potential difference across the right capacitor. And we will use that idea. So again, let's play our same song and dance. We would like the potential energy stored by an equivalent capacitor to be the same as the potential energy stored by the individual capacitors added together. But here, rather than assuming the charge is same for all three of these situations, or all three capacitors, we are going to assume that the potential drop across the capacitors is the same. Now we have to go back and look, but the equation telling us the potential energy associated with a charged capacitor and the difference in electric potential is given by 1/2, I'll write here C equivalent delta V squared. And again, we'll do the same thing, 1/2 C, the right capacitance, times the change in potential across the right capacitor squared, plus 1/2 the left capacitor times the change in potential energy across the left capacitor squared. But again, here we are going to use the idea that those changes in electric potential are all the same. And so we can, oh goody goody, cancel those out. Oh goody goody, we can cancel out the 1/2s. And we find out that we store the exact same amount of potential energy and have the same difference in potential, that's assumed, so long as the equivalent capacitor is equal to the sum of the individual capacitors. Or, if you prefer, again, more succinct writing, this happens for any capacitor that's in parallel. It could be 2 in parallel, 3, 4, 5, 6. And I apologize, I forgot to mention, I kind of, I incorporate this already into my brain, right? Parallel, think of it as you have options. right? In series circuits, if you go through one, you must go through another. Okay? To get to the 7th game of the World Series, you must go through the first 6 games. Alternatively, parallel, you have choices. Parallel, once you hit a fork in the road and you have a choice of going one way or another way. You're not required to go both. Okay. We'll define that more formally in the circuits class, but for right now, that's really what we need, is that you have choices. You can go one way or the other. Good? Of course, you can also combine these ideas. For example, I could have some parallel branch, which then has 2 capacitors in series. Something like this. And you can still use your rules for combining capacitors. You could, for example, combine those 2 because they're in series to find some equivalent. And then using that equivalent capacitance, then combine it in a parallel branch to find kind of like a total, if you prefer. That'll take some practice. And of course, we have homework assignments that help us out with that. But I just wanted to give you the general gist of the situation. So the last thing that I should discuss before we conclude this video is what happens when we insert a dielectric between the plates of the capacitor. Generally, we've been dealing with empty capacitors, or if you prefer air-filled, or for practical purposes, vacuum-filled. If you prefer, the dielectric constant between air and the dielectric constant of free space are very close together. So an air-filled capacitor is essentially, for all practical purposes, the same thing as an empty capacitor, one that's in vacuum. We would like to know what happens, first of all, to the electric field, or alternatively, the change in potential between the capacitor plates when we decide to insert some sort of material. Now, you already know what will happen. If I have a material, perhaps a material that starts out as neutral, but I expose it to an electric field, okay, you know that the positive charges will move one way in the electric field, the negative charges will move the other way. In other words, I will have an induced polarization within the material. So the electric field of the capacitor causes an induced polarization. So at any field point location inside the dielectric, we have 2 electric fields now, one due to the external capacitor, and the second due to the polarization of the dielectric material, the material that we've inserted. And so the net electric field is the sum of the 2. Now, incidentally, notice that the net electric field has decreased. It is smaller than the electric field of just the air-filled capacitor. Well, what does that mean? When we insert the dielectric, the overall electric field decreases. And if I'm thinking about the potential difference between the plates, does it increase or is it decreased? Yeah, good. Remember that the electric field is associated, the magnitude of the electric field is associated with the change in potential over a distance. Here I'll call it y. And so if the magnitude of the electric field has decreased, then so too has the difference in potential between the top and lower plate. And so because of the decreased electric field, I have less equipotentials between the 2 plates. Now, we should remind ourselves that, hey, that means if I define capacitance, the capacitance is defined as a charge over a change in potential. But because my difference in electric potential has gone down, that means my capacitance has gone up. My capacitance has gone up. By inserting the dielectric, what happens is that our capacitor is able to store more charge, assuming that everything else stays the same. So the plate area stays the same, the distance between the plates stays the same, everything stays the same. Comparing the air-filled capacitor to a capacitor that has a material, the one with the dielectric material can store more charge. That's particularly useful when space is of concern. For example, in a phone. The capacitors in this phone, and generally in any electronic system, are filled with a dielectric, and that allows us to store the same amount of charge, or excuse me, allows us to store more charge for the same physical size. Equationally, how we do that, we've already found that the equation for a parallel plate capacitor with vacuum is given by A epsilon over D. How we change this when we insert an extra material, as I've already previewed in lecture and that kind of thing, is that we change the epsilon. We include either what's called a dielectric constant, generally the variable kappa is given for that, or if you prefer, we simply replace epsilon naught with epsilon. So the permittivity of free space with the permittivity of a material. Either expression is perfectly fine. Please bear in mind, I believe our book gives kappa values, dielectric constant values. And so that value can be used to find the permittivity of the material. And like I said again, you'll see that coming in. I have also mentioned in lecture that epsilon, the permittivity of a material, is a rough measure of how much it polarizes in the presence of an external electric field. This gives you really a sense of what's going on there. Okay, I think that's plenty of information for the day. So we'll cut it quits. We'll call it quits here. I thank you for your attention. Keep up the good work. I'll see you next time.